you can look at it on the slides. Here with the fractions, we have also an implementation in the Maple package, in the Maple differential algebra package with François Boulier. One has to be a bit careful with the definition of these notions. So maybe just show you the algorithm here. Yeah. So that's the algorithm that takes the differential fraction and it isolates out what can be written as a pure derivative, as a first integral, plus some kind of minimal representation of what cannot be written as a total derivative.
Is that something related to Risch algorithm?
I don't see an immediate connection because here...
I mean, it's more complicated, so it's a generalization in some sense. So suppose your differential rational things don't have derivation in them. So it just becomes rational, right?
Yes, it's...
So if you integrate a rational, then you have Risch algorithm.
That's right.
So you should be generalizing that.
In the base case, this is true here, somewhere here, it would call the usual, one of the usual algorithms for integrating rational functions. That's right. Yeah? So that's one of the base cases here. Yeah. But it's not, I mean, it's a very simple case of the Risch algorithm because it's only rational functions. Yeah? So,
yeah, for you it's very simple. That's why I said it, but the Risch algorithm is not that simple.
Yeah, exactly. Yeah. Here the complication is really the presence of the derivatives.
It's kind of reduction.
Yes.
From generating to the Risch algorithm.
It reduces it to the base case of the Risch algorithm. Yeah, that's right. Huh? Okay. Yeah. So then let me go here to the end. Yeah. So that's just an application. Yes. So what we have done now is just the notion of integral differential polynomials in the very basic case of an ordinary differential ring. So it's no multiple derivations as yet. And also, it's only one indeterminate that I have added. But actually, in the other part that I have not had the time to go through, in the differential fractions part, there we have already allowed more than one indeterminate. But on the other hand, it doesn't have nested integrals. Yeah? So that's the formulation that has only differential fractions, and we consider antiderivatives on these. Yeah? But I would be interested in carrying this further to the usual case of partial differential polynomials with more than one indeterminate. And also the free object, okay, here I'm just saying that we have done this, yeah? For so-called regular differential algebras, this construction always works, and the differential polynomials are a regular differential algebra. Yeah? So it covers this case, and also rational functions, for instance, are also a regular differential algebra. And so apart from this, as I said, what is not yet really clarified is how you can constructively take this coproduct. Yeah? Because I said, if you have the free object and a coefficient ring, then you just take the coproduct and you get the polynomial. But because in the category of rings, the coproduct is of course clear. Yeah? It's just a tensor product. But in the category of integral differential rings, the coproduct is very involved. Yeah? It's like a bit like the shuffle. Yeah? You have to take alternately this, and then also take a canonical form. So an algorithmic description of this coproduct would also be an interesting thing.
Suppose the first thing to do would be to do coproduct of the shuffle algebras.
Yes, because they are...
Has that been done?
Actually, what you're saying is no. I'm actually discussing this with Lee. Yeah? The first step is actually what is the coproduct in the Rother-Baxter category itself.
Right,
yeah?
Right, exactly.
And that is, as you say, most likely
it's a commutative case.
Must be some shuffle thing. Yeah, right. Yeah. So that's because then we could really say that the new approach with the free objects subsumes the old one with the universal algebra, because at this stage it's not completely true, because the universal algebra approach gives a bit more, because it has all these coefficient rings inside, and the other one would work only if we had an algorithmic way of dealing with the coproduct. So that would be nice to close this circle.
That's right.
Okay, And another interesting thing that came out from this is this here. That's one thing that I have to mention here. the whole beautiful theory of extensions, of structure theory of differential fields, is something that as yet we cannot use at all. For the simple reason that an integral differential algebra will always have this ideal I. Remember this initialized function, it's an ideal. Now, if you have a field, bad luck, there's no such ideal, which means that in a differential field you cannot have a Rother-Baxter structure in the sense of an integral differential algebra. So one has to introduce something a bit different.
Are these integral differential algebra domains?
No, not necessarily. For instance, C-infinity functions would be an integral differential algebra. But you can impose this axiom. Then you would not allow smooth functions, but you would allow analytic functions, for instance.
Then that will become a variety once you put integral domains in.
That's right. But I mean, they are a variety. Integral differential algebras are a variety. That's not a problem. But if you impose this axiom, then it's no longer a variety. At least this part of the axiomatic specification would not be a variety. But the approach suggested by this quasi-antiderivative, so that means an outer inverse, or also called a quasi-inverse, because if you add the other axiom here, that f bar is an inner inverse, then this is called a quasi-inverse. And here, instead of the f bar, you have to imagine the integral. So it's like that. Then the other axiom here, you get a quasi-antiderivative, and that is probably the right kind of generalization that you need for describing differential fields, if you want to add to them some kind of integration, which would be important, because if you do boundary problems, you need some kind of Rother-Baxter operator. Okay, so at this point, sorry for being over time. We start,
So we'll push the schedule a little bit in the lunch hour and still have a 5-minute break. How's that?
That's